So this picture is actually relevant. It's going to be the only slide, the only picture in the talk. For those who know what is a Klosterman sum, this shows the way a Klosterman sum modulo 10,007 starts at 0 and ends up at this number here, which is a little bit larger than -2. It's normalized, so it fits the Weil bound. And it is a good illustration of the complexity of the kind of things we are going to talk about in these two lectures. So I'll switch this off. Succeed. And start. Can I light up the blackboard? Thanks. A little bit. Okay. So first question is, what are trace functions? So for people in analytic number theory, many of you have already seen talks about this, or looked at this, and many people have already an idea of what these are, but for the people in harmonic analysis, it's probably much less of a common standard topic, so I'm going to talk basically to the people who do not know what is a trace function and try to give some basic underlying ideas. So what it is we're interested in number theory, and mostly using analytical tools, and analytical tools intersect a lot with harmonic analysis of various kinds. And it turns out that there's one source of harmonic analysis that is extremely useful, that comes from a third area, which is algebraic geometry. So out of this, we get links with number theory, which turn out to be very closely related to harmonic analysis. So intuitively, so what's a trace function? It's a function on a finite field, or an algebraic variety of a finite field. So I call T the trace function. So in the simplest case, it would be just a complex valued function defined on K, which is a finite field. And in many, many, many applications, this finite field is just Z modulo Pz. And if you want to just think of that case, that's perfectly fine. And again, this is the simplest case, but in applications, it often occurs that you have more than one variable. So you could have a finite field to some power, or you could have points or some algebraic variety defined over P. But that should certainly not be what you think as the main case, or at least the V in many, 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 many applications would be something extremely simple. So typically just a fine space, or you would remove just a hypersurface, or you might just remove finitely many points, things like this. So it's perfectly fine to think of these two as the most important cases. So it's a function defined on this space. And so what makes it a trace function is that it has some kind of algebraic origin. It comes from algebraic geometry in a specific way. So it's somewhat difficult to give a complete definition. So, and even giving a complete definition, if one could do it in a few lines, would be just as unenlightening as Ben was discussing yesterday, just dumping on you the definition of nil sequences before you get some experience and understanding of what's going on. It takes a while. So, to get some intuition, it's best to think of examples. Because anyway, that's how these things arose. And one can think of examples as I'm going to describe. But before I give the example, I just want to at least explain why are they called trace functions. So there is a underlying algebraic mechanism behind that. But in any case, it's something that's worth keeping in mind. The value P of x at the point of the trace function is always the trace of some matrix, and that's why so it's a square matrix of some size which a priori can depend on x, and all its eigenvalues, which are not completely arbitrary complex numbers, lambda, which have to have the property, in the cases we care about, that the modulus of lambda is always the cardinality of the underlying finite field raised to a power which is w of lambda over 2, where w of lambda is an integer. So these are far from being completely arbitrary complex numbers. And before again I give an example, there's another very important thing to say. And again, we can make an analogy with some of what Ben was saying yesterday. So if I give you the full definition of trace function, basically it will just be a complex valued function, let's say on K with values in C, except for this kind of condition, but you can approximate any function as close as you want with no particular difficulty. So it's a finite amount of data, and it's not something that you can say anything about just like that. Like any function from K to C basically could be solved as a trace function. So to make this work, we need something like the complexity of new sequences. So there is a numerical invariant which we call the conductor of complexity, so it's C of t, which measures the complexity, the arithmetic complexity. And in most cases, what one really is interested in is a sequence of trace functions indexed typically by fp. So for every prime p, you have a trace function modulo p. And these have the property that the complexity remains bounded as p varies. And that's the essential thing that will make all kinds of estimates meaningful, as we will see in the most important case, which is the Riemann hypothesis. Okay. So I should say that this complexity was first defined by Touré, myself, and Philippe for functions in a single variable, and the definition for the general case more than one variable is way more subtle. It was done by Wilson a few years ago. Okay. As I said, all this is very theological until you see examples. So examples come in two classes. So basically, they are the really basic examples that occurred naturally in number theory starting from the time of Lagrange and Gauss, and Jacobi in particular. And then there's a whole kind of very, very powerful formalism that operates on trace functions. So you start with very, very simple examples, and then you operate with the formalism, and you get way more complicated examples. So the very basic examples are typically additive or multiplicative characters evaluated as rational functions. So let's take f, a polynomial or rational function with coefficients in fp. Okay. Again, you can think that k is fp. Chi, a multiplicative character. And let's say it's non-trivial. And psi, an additive character, non-trivial also, of k in all cases. Then if you take chi of f of x, or psi of f of x as functions of x, these are trace functions. Okay. And you should say that you take the value 0 at both, or zeros in the case of the multiplicative character. So the usual thing we do with Dirichlet characters evaluated at 0, Dirichlet character should be 0. And if you have psi of 1 over x, well, for x equals 0, you just send to 0. That's the natural thing to do. And it gives trace functions. And what's important, as I said, is the complexity parameter with complexity bounded in terms of the degrees only of the numerator and denominator. So in particular, if f is a polynomial, whatever the coefficients are, if it's of degree 10, the complexity will not change, well, will change, but will be bounded as every other parameter varies. Okay, that's the first example. Second example that I wanted to give. So let me immediately give some formalism. So there are two parts to the formalism. There's the easy part.
So the complexity does not see the conductor of chi?
I mean, chi is a character mod P, so its conductor in some sense is P. But that's a good point. So if you were thinking of taking modulo P for every P a character, a Dirichlet character, then you would say its conductor varies with P and is large because it's equal to P. But from the point of view of trace function, this conductor only sees the degree of f. So whatever character you take here, multiplicative character, from the point of view of the estimates involving trace functions, I will explain, the only thing that will matter will be the degree. I mean, if you've ever seen the veil bound for exponential sums, that's the phenomenon that's occurring. Okay, yeah, that was a good point. Okay, so formalism, there are two parts. There's the easy and there's the complicated one. The easy formalism, which really follows as soon as one knows the definitions of trace functions in the appropriate algebraic sense, is that you can sum trace functions, you can take the product, you can take the complex conjugate, and things like this. These are trace functions. And as always, we need to bound the conductors. And the conductors can be bounded quite easily in all of these cases, once one knows the definitions. That's the easy thing. And from the point of view of starting with these examples, for instance, it will give you multiplicative character of one rational function times additive character of a second rational function. It's the kind of thing that occurs quite frequently.
You should give him the first lecture this week, just so people know.
15 years of experience. Okay, that's the easy formalism. And now there's something much, much deeper. And this is something due to the Lim. More or less exactly 30 years ago. So Delin observed that the formalism that algebraic geometers of the quatentic school have developed implied that the class of trace functions is stable by discrete Fourier transform. So if you have a trace function in any number of variables, but on an affine space, so k to the d, then So I normalize the Fourier transform unitarily, because that's the most convenient for applications. And this normalization is the square root of the size of the group that you're summing in. Then you sum over x, p of x, psi of x in our product with y. So psi is a fixed additive character. Okay. So if k is fp, you would just take the usual exponential 2i pi x over p, for instance. Then this is also a space function. Okay, and so this in Delin's formulation was all you needed to know for certain purposes, and this is how it was mostly used by algebraic geometers, in particular Lomont and Katz, in all kinds of ways over the years. But for us, for analytic number theory, we need to bound the conductor, and this is something that we did with the conductor bounded in terms of the conductor. In fact, linearly, if you define the conductor correctly, so this was observed by Fouvry and Philippe and myself for d equals 1, and it follows from the definition of Sawin in the general case. So if you think about this, and even with the very, very basic qualitative information that the value of a trace function is the trace of a matrix with eigenvalues of a certain kind, this is highly non-trivial. And if you know a little bit more about the properties that this is supposed to satisfy, this is a very, very deep fact that they will prove. So this contains, if it's stated with full strength, this contains very general form of the Riemann hypothesis of a fragment. So, as an example, let's take one of these basic things and compute the discrete Fourier transform. And what you will get would be something like this, for instance. I take k to be fp, the usual additive character, and I take the Fourier transform.
Square root of p.
Square root of p, absolutely, that's Q. So what I've done here, I've taken the trace function t of x to be e of 1 over x over p. Well, x bar over p. So x bar is the usual notation for the inverse of x modulo p. So this is a trace function by the first example, and this is the Fourier transform. This is a Klosterman transform. As defined by Poincaré in the 1910s, and Klosterman pretty much exactly 100 years ago. Okay. And so together with the bounds coming from the Riemann hypothesis, which I will restate in a different way a little bit later, one gets for free out of Delin's theorem here that these are bounded as the parameter y varies and as p varies. So if you do it this way, you do not get, unless you look carefully at the bounds, the veil bound for Klosterman sum, which would say that this is bounded by 2 in modulus. It's between -2 and 2 because it's a real number. But what you get essentially for free out of this theorem of Delin, and that illustrates how strong it is, you get for free that the Klosterman sums are absolutely bounded as all the parameter varies, which is already, for many, many applications, would be more than what you need.
Hidden in here is that you have these, the eigenvalues have these.
Right, so the thing is, what I didn't say is that there's this notion of purity, which says that all the eigenvalues have the W of lambda being the same. And Deligne proved that if this is the case for T, this is also the case for the Fourier transform, with proper understanding. There's some subtleties, but that's essentially what it is. So if you start,
need to know what the weight is.
yeah, but so this is a weight 0.
Yeah. So
And the Fourier transform preserves the weight when you normalize it the way I did.
Ah, okay.
So you get from weight 0 to weight 0, so you get exactly that. Yeah. Yeah, I didn't mention it, but it will also show up again in the next section. Okay. And so now you see you can really build already just out of this many trace functions. And in fact, you can build just with what I've stated, most of these that tend to come up most naturally in analytic number theory. At which point the one natural thing that people think about is, why should we care about the underlying algebraic formalism and not just try to work and define trace functions and have a theory which is just based on examples plus operations. And that's a natural idea, because if, after all, in most of your applications, you only see what happens by taking 2 or 3 examples and operating this kind of way, you might say, why do I need to know the general definition and so on? And the problem is that in the proof of the theorems, sometimes you actually make manipulations which will destroy these kind of classes, and one knows that there are lots and lots of trace functions which are not obtained by this procedure. So that's at least for me, the main reason to look at the actual definition. Okay, so now let me state the Riemann hypothesis in a way which is recognizable as an harmonic analysis statement. So it's a theorem of Deligne. This is the second version of the Riemann hypothesis of a finite field, which was published in 1981. But it's reinterpreted in a way that makes it well adapted to analytic applications. So I will first need a small definition. So one which will be almost a rigorous definition, the other one will be slightly not very precise. So we will say that T is of weight 0 if all eigenvalues of the matrix theta of x at all x have weight W of lambda equals 0, which means that their modulus is 1. So basically, you should think of something of weight 0. That means that the value at a point is the trace of a unitary matrix, essentially. There are some subtleties, but that's mostly what we can think about them. And then there's a necessary condition, which is that one needs to think, one needs to know what is a geometrically reducible trace function. So, and this is where my definition will not be super precise. So I assume that T has weight 0. So I will assume I'm already in this case. So that's definitely the case where you take E of x power p, for instance. So if you take something of weight 0, it's going to be geometrically reducible. That's a condition that looks a bit complicated when you write it purely in terms of the actual algebraic underlying objects. But one way to think about it is basically that the L2 norm, discrete L2 norm is 1. Well, on average, so it's that the sum of modulus of T of x squared should be k plus an error term, which is a bit smaller. I can just say equivalent to this. That will be precise. Okay. But equivalent means the constant is 1. Okay. It's not of order of magnitude k, it's k plus something smaller. So it's not a rigorous definition, but it's certainly good enough to understand what's going to come as the analytic expression of Deligne's Riemann hypothesis, which we interpreted with Fouvry and Philippe as a form of quasi-orthogonality. So precisely, let T1, T2, so it's a theory that works best for one variable function, so I'll state it this way. There are versions in more than one variable, but they are more complicated to precisely understand what they mean. So you take T1 and T2, two trace functions in one variable, which are weight 0 plus geometrically reducible. Then one of the following things happen. The first one is that they are the same, essentially, like before this causation. Precisely, there exists a complex number alpha with modulus 1, such that T1 is alpha times T2. That's the first possible case that can happen. And if that's not the case, there is no correlation. Meaning that if you look at here, it can be more readable. If you look at T1 of x, T2 of x conjugate, so we try to understand the correlation of the two trace functions. Now, we all know that correlation is not the same as causation. Well, in algebraic geometry it is. So if they are not exactly the same, they're actually completely uncorrelated. And in fact, it's big O of square root of the size of k. Square root cancellation with implied constant, depending only on the conductors of T1 and T2. And in fact, basically a multiple of the product of the two works fine. Okay, so as I said, so from the harmonic analysis point of view, this is a kind of statement saying that, of course, when T1 is alpha times T2, this is just going to be the sum of modulus of T1 squared times alpha. Geometrically reducible tells you it's exactly of size k. So this is saying that either the two things are exactly the same, and there's perfect correlation, or there is no correlation in a very strong sense. So it's quasi-orthogonality in a very, very strong sense. Because of course you cannot do better in general than square root cancellation, which is what you get here immediately from the Riemann hypothesis. And if you're wondering where does this come from? How can we get such an extraordinary thing that you have either equality, full equality everywhere, or a complete decorrelation, which is not something you would get in many, many other circumstances. It's because of the underlying algebraic mechanism that's behind it. So in some sense, these are kind of approximate characters. The trace function can also be seen as being the characters of some group evaluated at very specific elements. Characters of a compact group satisfy orthogonality relations. And this is what we see here in this statement. We are replacing the integral over the whole compact group, which would give perfect orthonormality, with a sample at various points given by Frobenius elements, which are what gives rise to the trace functions. And these Frobenius elements are so well distributed that you still see approximate orthogonality, equidistribution in some sense. This is what's behind this result, or one way to interpret it. So the proof is very, very sophisticated. This is the main achievement of Delisle's work on the Riemann hypothesis. It's not quite the most general version of the Riemann hypothesis, but it's actually, I think, equivalent to it by using the rest of the formalism. And for analytic application, this is definitely what comes up the most. Let me give you one two examples. So let's take T2 is 1 and T1 of x is E of x power t. say, plus y times x. Y is a parameter in f star. Then the sum of T1 of x, T2 of x conjugate is the first common sum. T1 and T2 are not the same. And so it's we go of square root of taking k equals x. So we recover again, and that's pretty much why this theory of the Fourier transform also gives a very strong bounds by an application of these kind of things to situations where you put an additive character in the picture plus some extra kind of algebraic miracles that happen. Okay. I'd like to tell another example. Yeah. So, and there's nothing special with this. You could take any rational function that's non-constant mod p. You would get the same thing with a bound that only depends on the degree of the numerator and denominator, because the conductor only depends on that. So again, you recover out of this, without having to know it, you recover the veil bound in very, very great generality in a way that's quite convenient for analytic applications.
But so far you haven't shown anything beyond that. This is 1948. So far.
Yeah, but you just do a Fourier transform in d variables with d at least 2, and then you're in business. That's just to, yeah. Okay, let me give another example, since I think I do have a fair amount of time. Okay, now one reason, as I said, this applies well to analysis, non-theory and harmonic analysis. Well, there's a lot of harmonic analysis that's based on L2 or correlations, and this shows that trace functions have a very, very, very good L2 theory. And they have a formalism that's also extremely successful. So you can use that to study, for instance, Gauss norms of trace functions. And what happens is that, like the sketch of the proof of the inverse theorem for Gauss norm, that quantitative that Ben gave at the end of his lecture yesterday, all the steps where he more or less said, well, there's some extra work, there is approximative and so on. Basically, you take the same argument, you just run it through, and everything is exact. So you get an inverse theorem of the form. So if T from, it works best over Fp, so let's do it over Fp, is a trace function of weight 0, let's say geometrically reducible. Then either the UD norm of T is as small as for a random function. So in other words, basically as small as it can be, which must be something like p to the power minus 1 over 2 to the d, up to shifting d to d minus 1 or d plus 1 as usual. Or t of x is proportional to a polynomial phase for some alpha with modulus 1, and f a polynomial in Fp of degree at most t minus 1. Okay. So it's literally an exact inverse theorem, as good as you could potentially imagine. The only obstacles to small Gauss norms are coming from the expected phases. And the proof is basically taking the ideal proof, like the one that Ben presented, and then running it through, and where you would have to do a lot of work in the classical case. You typically apply this, because once you have non-correlation, you actually have causation, and it makes things quite simple. There are some technicalities, of course, but that's really, compared to the inverse theorem, then describe. This is really very, very, very easy. So actually, we have never tried like these new multi-dimensional Gauss norms. That makes perfect sense to look at a function into variable, that's a trace function, and try to look at some of those that Sarah was describing. And it could be that one can say something. So that's something also we might try to work on. Algebraic things that occurred in Sarah's talk will occur also very naturally from the underlying algebraic mechanism. That would be interesting. Okay. So this was all about, in some sense, the theory of complete sums. And the title of the talks is really about short sums, so now we're going to discuss short sums.
Are there any new sequences coming up in the goals?
Sorry, I didn't hear.
Are there any new sequences coming up in the goals?
No, we've never seen any. It's interesting from this point of view. We've never seen anything. There are some questions which are not entirely clear. It's when you take T to be somehow a very, very large conductor. So here I say as small as a random function, there's an implicit constant which is bounded by the conductor. In terms of the conductor, one can try to make this become a bit large, and then the picture is not so clear. And there could be some nil sequences, but I don't.
Your result is basically saying that any null sequence that's got anything to do with a trace function.
At least in this setting, yeah. In this setting where p goes to infinity and the conductor is bounded, yeah. There's no nil sequences. It's just the ideal situation where you have actual polynomial. Yeah. Okay, so section 4 is short sums. So in applications in analytic number theory, one quickly learns that it's very often not the full complete sum over the whole parameter space of the trace function that comes up. One often has to deal with short sums. Say, in the case of Fp, you would sum over x between 1 and some parameter n of the trace function, where n is strictly less or is at most p, and typical case is n is a fixed power of p, where the exponent is strictly less than 1. So this was already, let's say, when Klosterman used Klosterman sums to study representation of integers by diagonal quaternary quadratic forms. He did not get Klosterman sums in their full complete glory. He got things which were short sums. And then he applied some techniques which allow you to sometimes study the short sums instead of long sums, which work when theta is not too small. So here are some examples. So a very simple example is the problem of the least quadratic non-resisting mode P. So here, you want to find the smallest integer n, which is not the quadratic residue modulo prime. And the usual way to study this is to try and get a non-trivial bound for a sum of Legendre symbol n over p, which are 1 when n is a prime of p. And you want this to be strictly less than n for n as small as possible. And it's conjectured that this should be true when n is an arbitrary fixed positive power, but we are very, very far from that. That's a short sum. Here is another example which is less important, but I like it, so I'm going to mention it. It's a theorem of Will and myself. It's related to the picture I gave at the beginning. So the picture I showed at the beginning was, as I said, you look at a Klosterman sum, modulo prime, and you look at the partial sums, so starting with 0 term, 1 term, 2 terms, so on, and you join these by segments in the complex plane, and you look at the resulting picture and you try to understand if the full picture as a function from 0, 1 to C has a good statistical behavior. So in other words, given a prime P, a y invertible by P, we define a function k P of y. So it's a function, continuous function from 0, 1 to C, continuous, and it's obtained by linear interpolation by saying that if I take I over P minus 1, then I send it to the Klosterman sum, but just the partial sum for x from 1 to I. So if I take I equal P minus 1, that tells me that 1 goes to the full Klosterman sum, and if I take I to be P minus 1 over 2, I get the middle point of this picture that I do. And we think that we're doing this when P is a very, very large prime, and Y is taken uniformly at random among the P minus 1 invertible classes of P. And we ask ourselves, is there a good limiting distribution for these as functions? So it's related to some very important topic in studying trace functions algebraically, which are equidistribution theorems in the style of Deligne and Katz. But we do it for sums which are not the full length. And what we prove with will, among other things, is the following conditional result. So the conclusion is that these functions behave statistically like a specific explicit random Fourier series. So it's of the form some constant term plus the sum over h non-zero of e ht minus 1 over 2I pi h STH, where all the STs for I and Z are independent semicircle or Satotate distributed, whichever you prefer. Depending on your taste. Or minus 2 to 2. So it's a semicircle from minus 2 to 2. Anyway, it's not very important what it is. It's some very specific, very concrete random Fourier series. We cannot prove this quite yet. We can do this if we can bound the partial sums of the Klosterman sum on intervals of lengths a little bit less than square root of p. Provided there exists a positive delta such that one has, I'm not going to be super precise, no trivial bound for the sum for x in I, e of x, y plus x inverse 1p, divided by the square root of p, for I, the image modulo p of an interval of length bounded by p to the 1/2 minus delta. And as I will present in the next few minutes, this is a critical case in the sense that if we could take delta equals 0, this would be true for relatively soft Fourier analytic type of reasons. But for slightly smaller interval, it becomes an extremely challenging problem to do this and to do an appeal to authority. So Bourgain saw the paper and tried it, and as far as I know, did not succeed. So, Boolean tried. I don't know how they tried, but he sent me some email where he did some variants, like if you average over P a little bit or things like this, then you could make it work. But for fixed prime, this sounds like a very, very hard problem.
And by non-trivial, you just mean?
We needed a small power. I mean, I think if you got something that's non-trivial, meaning little o, probably one could use it by using sufficiently sophisticated probability theory to deduce the theorem, but to get it naively, you need small power.
Okay.
Yeah. I think a log probably might not suffice. I'm not quite sure. We didn't try. So what we did is, with will to get something unconditional, we use cluster sums with two parameters. So instead of just xy plus x bar, we had xy1 plus x bar times y2. These are natural from the point of view of applications, and this extra parameter makes the averaging possible. So we got the unconditional convergence, and that's what was displayed in my picture.
Just for intervals of length exactly square root p, do you know any non-trivial?
So the only thing we know for this, as far as I know, is when the length is a little bit larger than square root of p, we have the usual probability of Pinot-Gradov type thing, which I'm going to state in great generality.
And you need uniformity in y?
Yes. Yeah, it has to be uniform in all parameters, but including the interval.
For an incomplete Klostermann sum, this would be possible, right? If I remove the xy and just look at the incomplete part.
You mean just the x bar over p?
Yeah.
Yeah, there are results here of Garayev and people like this. At the time we looked, and like what's known does not yet suffice for what we. I mean, and of course Bourgain would have told us if that was a direct corollary of what he knows or knew. So that's a problem. In fact, we don't need for individual things. We need a force moment. A force moment when you average over y. That should be way easier. And even that, and that's what Bourgain tried, and even that seems to be very hard. It transforms itself into another kind of similar exponential sum. It's kind of, I mean, it's kind of obvious to people in additive combinatorics. I think once you do the force moment, you have something like additive energy of the inverses of the y's in some interval of relatively small length. Which there are things that are known about these kind of questions, but as far as I know, this particular case is not known. Anyway, if anybody from harmonic analysis or additive combinatorics can solve this, that would be very, very nice. Because I think this theorem with will is maybe one of my favorites of my own thing. And it's always a bit frustrating that the most natural statement we cannot quite do yet. So, what do we know about short sums? We know some things, but not that much. But when we don't know things, we make conjectures. And let's make a big, broad, very powerful conjecture, if it's correct. So it's, in some sense, a folklore conjecture. In another sense, it's something that's not yet been really very often stated explicitly, so I think it's worth stating it a few times until we find someone with an idea to do it. So let's call this the short sums conjecture. We don't have a snappy name for it yet. So based on the examples we know, based on wishful thinking, and the fact that there is no obvious Carter example, we can make the following conjecture. So we're going to be in the situation of Berlin's theorem, but we're going to do it with short sums. So trace functions, T1 and T2, not P, in one variable. Let's say they are weight 0, geometrically reducible. Okay, and so what we want is conditions that ensure that we have the same dichotomy, causation, or correlation. So either, now we're not going to claim square root cancellation, because we're careful people.
Oh, it's an assumption.
I haven't put the assumptions yet. I'm trying to build to the statement. So
But
we're
it's
going.
I.
Yeah, of course. I'm actually going to just do it in some interval, which is the initial interval, which because of the formalism is actually in that case not a restriction. But let's do it this way. We're going to want to gain a small power of the length if n is larger than some power 1 over d of p, unless, so when can this not be a true statement? So suppose that T2 is 1 and T1 is phase of an additive character of a polynomial of degree less than d, and you take the initial interval and you take small coefficients. There is no cancellation in the initial segment, so you cannot have something like that, unless T1 x T2 context conjugate is proportional to an f of x to p for some polynomial p, let's say fp of x of degree less than or equal to d. And so we pick d at least 2 to do this. I think it probably, d at least 2. And we pick an epsilon positive. And then we claim there exists delta positive, depending only on epsilon. And we want the constant here to only depend on C of T1, C of T2, and maybe D.
What is this?
D is something you pick here. So, in other words, it's a little bit, suppose you take D equals
D is
2.
not related to T1 and T2.
No. So, let me give an example to see what this means. Because the thing is, in this case, there are these counterexamples, like E of x squared over P has no cancellation on some intervals of length square root of p. So, suppose you want to sum a function, a trace function, on an interval of length square root of p. Then you take d equals 2, essentially, and this will tell you that unless your trace function is of the form E of a polynomial of degree 2, there will be some cancellation in the sum of length square root of p. So this is an absurdly strong conjecture, if it's correct. I mean, Cooley had some papers where this thing that called, I think, hypothesis R star, which was the very, very special case where you take E of x bar over P as a trace function. And this had already amazing consequences. Of course, it implies trivially the conditional result that I mentioned with the shape of the cluster sound, and so on and so on. So let me give some examples. How much more time? Right. So there is a very, very general thing which is known as the case d equals 2. I'm sorry, d equals 2. So what does it say when the case d equals 2? We have lengths a little bit larger than square root of p, because I put this small epsilon. And in this case, it says that, I guess here I should say strictly less than b. So this is saying that if you sum a trace function, so I'm taking t2 equals 1, from 1 to x, you get some cancellation, unless, so t being weight 0 irreducible, is an additive character. So if you take a multiplicative character, that's not an additive character, then that tells you that the sum of k of x for x from 1 to p to the 1/2 plus some epsilon is big O of this thing to some small power, and this is a very general form of Polyavino-Gradov. In great generality, and this is true. Okay, so this is true for Polyavino-Gradov, meaning for Dirichlet characters. This goes back to Polyavino-Gradov, and for other special cases, it has been done in an isolated way, and this is one of the results from our first paper with Fourier and Philippe. And one can say what is this delta, because the actual bound is going to be square root of p log p. So one can even say that n doesn't have to be really square root of p times another power of p, some logarithm is enough. So that's the most general evidence we have, I think, in full generality for this conjecture. It has lots and lots of applications. The proof is basic harmonic analysis. So you interpret the sum as a complete sum, modulo all of prime, all the x of t times characteristic function of the interval. Discrete Plancherel, this is the sum of the Fourier transform of the interval times the Fourier transform of t. Delin tells you the Fourier transform of t is still a trace function and is still behaving well. You decompose in discrete Fourier, you compute the Fourier coefficient, and you get square root of p log p as an upper bound for whatever interval you have, and it's non-trivial in that. So it's really kind of straightforward. If you don't care about very special constants, like there are very refined forms of Polyavino-Gradov where people care about the constant and everything. If you don't, it's completely elementary harmonic analysis. Then, what are some examples we know? As far as I know, cases where we can do everything, meaning an arbitrary d, do exist, but they are very rare. So you can do trace functions which are themselves additive characters of polynomials. This is going to be Weil differencing or Van der Korput or Vinogradov methods of exponential sum. But Weil differencing is enough. Where you get a very, very small gain in very, very short sums, unless there is some obvious reason, which is exactly that one. The other case that I know where something is known for arbitrary d is the work of Bourgain and Delichou, Konyagin, and Variant. There are also papers with Chang, and there's work of Kedov, which simplifies this a bit, which is about essentially, it's not quite literally maybe the trace function in the precise sense I was describing, but it's essentially the characteristic function of a multiplicative subgroup. So it's not quite literally this setting. We're not summing over an interval. We're summing an additive character in this theorem over a coset of a very small multiplicative subgroup, but one gets results, non-trivial bounds, even for very, very, very small multiplicative subgroup. And this is, of course, based on additive combinatorics, which suggests strongly that additive combinatorics should have a lot to say about the general case. And I think I'll probably stop here. So the last remark, so Philippe will mention some other examples at the beginning. Like the Burgess bound is the other super well-known case, but Philippe will mention that. The one thing which is also intriguing, if you remember what I said about the inverse theorem for Gauss norms for trace functions, these are exactly the same conditions. And combined with this, that really gives the idea that somehow additive combinatorics should come into play if this conjecture needs to be proved. I mean, it might be false in this full generality, but there's no question that it's going to be true in also considerable subcases at least, which should be enough for many applications. If there are lots of applications, we would just need to apply this with a fixed value of d for fixed trace functions. So even if the full thing is completely wrong because there's some clever counterexample, it would still be potentially interesting. Actually, if there was a counterexample, it would be very, very, very interesting. I think even the algebraic geometers would be extremely interested by the trace functions that would fail to satisfy this, because they would have to be very, very unusual from the arithmetic geometry point of view also. Okay, so I'll stop here.